When filtering contaminated water with biochar or raw biomass, the efficiency of the process depends on a single metric, the point of zero charge, or PZC. This metric represents the exact pH boundary line where the material's surface charge flips from predominantly positive to predominantly negative. To find this threshold, we are going to walk through the pH drift method, a standard lab procedure that generates a precise graph to pinpoint your material's electrical zero crossing. First, you need the right setup. This includes your solid adsorbent, like biochar powder, a background electrolyte, dilute acids and bases, a precision scale, Erlenmeyer flasks, and a calibrated digital pH meter. With this equipment prepared, we can stop guessing at our filtration parameters and start actively measuring the electrical state of our materials. Step 1 is preparing the background electrolyte. You will aliquot exactly 50 milliliters of a 0.1 molar solution of sodium chloride into 6 to 8 separate Erlenmeyer flasks. This background solution is required because it locks in a constant ionic strength across every flask. By doing this, we guarantee that any charge variations we measure later are caused strictly by pH changes rather than variations in the water's chemical concentration. Step 2 is creating a pH gradient. Using dilute hydrochloric acid and sodium hydroxide, adjust the liquid in each individual flask to a unique pH value, creating a wide spectrum that spans from 2.0 up to 12.0. Look at this data table. Before proceeding, you must precisely record this initial baseline pH, called pHi, for every single flask. Without this starting data, the final calculations will not work. By establishing this artificially wide, highly controlled gradient of pH environments, we are building the foundation required to force the adsorbent material to reveal its specific buffering behavior over the next steps. Step 3 introduces the active material itself. Weigh out a precise, identical mass of your solid adsorbent, typically 0.1 grams of biochar, and add it to each of your prepared flasks. For step 4, move the flasks to an incubator shaker set to a constant 25 degrees Celsius and a moderate speed of 150 RPM. You will leave them to equilibrate for 24 to 48 hours. Before you walk away, there is a critical failure point to check. You must tightly seal every single flask prior to incubation. If you leave the flasks open, atmospheric carbon dioxide will dissolve into the liquid. This generates carbonic acid, which alters the pH of the solutions and corrupts the entire dataset you just spent time setting up. Hermetically isolating the system from the atmosphere is the only way to guarantee that the final pH shifts are driven exclusively by the protonation and deprotonation of the biochar's surface. Step 5 happens after the wait is over. Remove the flasks from the incubator. To get an accurate measurement, you need to isolate the clear supernatant by filtering or centrifuging the samples, rather than trying to measure a turbid slurry. Take your freshly calibrated pH meter and measure the final pH, or pHf, of the clear liquid from every single flask, making sure to record each value carefully. Step 6 brings us to the math. As you can see in this equation, you calculate the total change in pH for each individual sample by subtracting the initial pH from your newly measured final pH. This gives you the delta pH. Now we plot this data, and we have to ensure the axes are placed correctly. The delta pH goes on the y-axis, and your initial pH, pHi, goes on the x-axis. With the axes set, you can map the calculation from every flask onto the grid. A smooth curve connects your plotted data points. To identify your point of zero charge, trace that curve exactly to where it intersects the horizontal zero axis, where delta pH equals 0. That specific geometric intersection is the physical manifestation of the point of zero charge. It takes all of your raw, disparate lab measurements and translates them into a singular, actionable system metric. Now that we have calculated this specific value, we can use it to configure a physical reactor for actual contaminant profiles. Here is a model of our active biochar. If you are targeting negatively charged anions like hexavalent chromium or fluoride, you operate your reactor at a pH below your point of zero charge. The acidic solution heavily protonates the biochar surface, coating it in positive hydrogen ions that pull in the negatively charged contaminants. If your target is positive heavy metal cations like copper or lead, the mechanics reverse. You keep the reactor pH above the point of zero charge to deprotonate the surface. leaving it coated in negative oxygen ions that pull heavy metals straight from the solution. Identifying the point of zero charge provides the data needed to select an operational pH where the material's surface charge actively attracts the target ions.